Let us look at the climate effect of aerosols. The first one is the black carbon. The main sources are incomplete combustion and the open biomass or biofuel burning. And what is the effect on the climate when we look at it? Absorbs high proportion of solar radiation, and this leads to warming of the climate system. And when we talk about the sulfate, the main sources are oxidation of sulfur dioxide. And what is the effect on the climate? It absorbs negligible solar radiation. It cools the climate by scattering solar radiation back to space. So this is having a little bit positive effect. And what about organic carbon? The main source of organic carbon is co-emitted with the black carbon during combustion. Both scatters and absorbs solar radiation. The main effect is it both absorbs and scatters solar radiation. It has some cooling effect as well as warming in other cases. The more pronounced warming effect is highly reflective regions like the Arctic. So here are some of the studies which many people had carried out to understand the annual cycle. These are all the annual cycle studies that have been used for understanding the long-term trend changes. So the one is related to black carbon measurement, then aerosol absorption coefficient, sulfur oxides, non-sea salt sulfates, and general observation. So based on this tree chart, we can understand what is the long-term trend analysis of aerosol data. So these are carried out by various scientists and their names are given. More details about this chart will be given in the textual content. Let us look at the characteristics of organic carbon. The organic compounds that are not so refractory are heavily conjugated to be essentially non-volatile, and black can still absorb light, and they tend to absorb more light at shorter wavelength, that is in the blue region, and less light at longer wavelength, that is in the red region. The light that passes through will be reddish orange or brown, that is why it is called as a brown carbon. Unlike the black carbon, the brown carbon can be semi-volatile and it can either consist of primary material, often from the same combustion sources producing black carbon, or it can be produced via atmospheric chemistry as secondary brown carbon. And some of the secondary reactions involve bases such as ammonia and constitute the classical browning reaction from organic chemistry that also cause fruits to brown when exposed to air. Although the brown carbon is chemically active atmospheric constituent, its formation and modification are much more complex and less understood than the non-reactive black carbon, because brown carbon keeps on changing. So it's very difficult to study the brown carbons compared to black carbons, which does not change that easily. The global budget for black carbon is uncertain and controversial. It is possible that regional differences in brown carbon sources may partly explain the difference between bottom-up and top-down emissions estimates of total light-absorbing carbon. Because when we talk about carbon, both black carbon and brown carbon are included. So we are unable to differentiate between the contribution from black carbon from the brown carbon. So that is the reason it is always difficult to quantify the effect of organic carbons in the climate change mechanism. So here are some of the indirect climate change mechanisms. One is influence on snow and ice, mainly the black carbon. So the effect is it amplifies the ice melt. When more black carbon is falling on the ice, it will absorb solar radiation. So that's the reason that leads to warming, which leads to melting of ice. The mechanism is this actually lowers the albedo and increases the solar heating of the surface. Lowers albedo means it does not reflect the solar sunlight when it falls on it. So that's the reason it starts warming the ice, leading to melting of the ice. And impact on the cloud properties. What are the major cloud effects? One is the parameters that are affected are droplet size are affected, lifetime changes, and vertical extent also changes when black carbon is present. So these are all the changes that is happening. And how does it influence the climate? Short wave cooling and the long wave warming are there, because we have seen some part of the black carbon can absorb light and some part may scatter light. So that's the reason cooling and warming are there. And in the global context, indirect cloud forcing like larger than direct forcing. So these are all the different ways by which the black carbon affects the climate. And when we look at the Arctic specific impact, the unique characteristics are basically the extreme seasonality of solar radiation, because in the winter we have hardly any solar light falling on the Arctic region, and we also have 24-hour sunlight. So that means we have extreme seasonality of solar radiation in the Arctic region, and high frequency of mixed phase cloud is also present there, and these are rapidly evolving sea ice distributions. So this affects basically the sea ice distribution. So these are all the unique characteristics specific to Arctic, and some of the phenomena is this leads to actually a complex and unique effect on the Arctic aerosol abundance and climate impact. So that's the reason we always try to understand what is the mechanism by which the aerosol affect the climate in the Arctic region. Some of the effect of short-lived climate forces in the Arctic. One is the changes in the Arctic condition, which include reduction in the sea ice extent, thawing of permafrost, humidification of the Arctic atmosphere. The first two are basically responsible for the Arctic amplification effect, and the third one is actually leading to the formation of more cloud, which leads to snow or precipitation in the Arctic region. And what is the impact? This affects the emissions, this alters the lifetime of the clouds, because the short-lived climate forces affect both the climate as well as the aerosol and the cloud formation. This also influences the radiative forcing. And here is another tree line chart which talks about the temperature and the radiative forcing estimates. The complete details are given in the e-text for you to learn. Very few things we will see. One is about the black carbon emission response. So in the Europe and the North America, there is a 0.0 to 0.1 degree increase is observed, and in the Asia 0.05 to 0.08 degree increase in the temperature is observed because of the radiative forcing. And global sulfur emission relates to 0.02 to 0.025 degrees centigrade change of temperature or increase of temperature. These are all studied by various scientists, and each paper describes about the observed phenomenon what is shown here. Similarly, there are more studies which talk about the geographical and temporal variation. Sharma et al. Had found that winter pack for anthropogenic tracers they have studied, and they also included natural tracers like methane sulfonic acid, iodine, mineral dust, and sodium chloride, and winter maximum. So these are all the natural tracers they have studied. Quinn et al. Had studied about annual cycles of anthropogenic haze tracers and at different stations in the Arctic region. Eichhardt had studied about annual black carbon and sulfur oxide data for model evaluation. Beckman studied about ethylometer, that is for the black carbon. This is mainly used for the measurement of black carbon. Schmiester had studied about seasonal cycles of aerosol optical properties, and Moshes studied about pan-Arctic source appointment and major ions black carbon and organic aerosols summer and the abundant in the winter. So all these aerosol types they have studied, and they try to understand how the aerosols and the short-lived climate forces affect the climate change in the Arctic region.